So lecture number 2, measure theory. So in the last class, we see that what is the definition of the union of sequence of sets, so I equal to 1 to infinity. What is the definition of, say, I equal to 1 to intersection of I equal to 1 to infinity? So these are very important, and obviously there is a union of the arbitrary collection of unions. So I belongs to I, the index. That also is, and we know what is the definition of that. What is the definition? And the last thing is that x belongs to the intersection such that x belongs to ai for all I, and for union is just at least one I. So we know these definitions, and we know what is called sigma algebra. Now we deal with some important concept. Is called limit of set. So limit of set, sequence of set. Now consider a sequence of set. It is not an arbitrary collection. It is just collection. Is just index set is natural number. So a1, a2 is a collection of. It is a sequence, not a collection, because there is a ordering. What is the difference between sequence and set? In the sequence, there is a ordering. A1, A2. The A1 is the first element, A2 is the second element. But in set, A1, A2, A3 set containing A1, A2, A3. There is no such first and second or third. But if I say it is just a sequence or order triplet 1, 2, 3, that means the 1 is the first element, 2 is the second element, and 3 is the third element. Now, the De Morgan's law, everything is clearly true. That for any arbitrary collection also, so it is for De Morgan's law. It's just intersection of I belongs to I, ai complement, and similarly for the other, the dual thing, intersection and then complement. Now we will define two concepts: a lim sup as n tends to infinity, a n. What is the meaning of that? That meaning is actually, by definition, n equal to 1 to infinity intersection, and then first union, then intersection, k equal to n to infinity a. So this is just definition. So what is the motivation? Why this definition? We take this definition. The idea is this. So first of all, just think what is this first. So what is this? So there is a sequence, and then a1, a2, dot 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 dot, dot a3, dot 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 dot. Now we are taking the union over all k equal to 1 to infinity, n equal to k equal to 1 to n to infinity. So for the first one, if n equal to 1, what is the element? So you just take as a bn, write this as a bn. So what is bn? Bn is nothing but the union over k equal to n to infinity an. Now what is b1? So b1 is just union over all this set. So it is union over all this set. Sorry, k equal to 1 to infinity. So union over all this set. Now what is b2? b2 is just 1, you just drop 1. It's just union over 2 to infinity. You drop 1. You're just dropping 1. What is b3? You are again dropping 1 more, a2. You are dropping 1, a2. So that means what happened? That means your b1 is a subset of b2. Maybe equal, maybe a1 is actually the elements of a1 maybe in some a2 or maybe in a3. In that case, it's maybe equal, but it can't be a superset. So b1 is a subset of b2, because in b2, oh sorry, it's the other way. B1 is a superset of b2. So because we drop a1 in b2, so this is a decreasing sequence. So that means it is a decreasing sequence. So it is bn plus 1 is a superset of bn. Oh, sorry, the other way. Bn is superset of bn plus 1 for all n in natural number. So that means it is a decreasing sequence. So bn decreases. Now what we define in limit? So we define if it is a decreasing sequence, the limit of bn, n tends to infinity bn, is just we define like that, is the intersection over all this n equal to 1 to. So this is the definition of limit for a decreasing sequence. So if it is a decreasing sequence, so what happens? What is the Venn diagram? So this is a B1, then it is B2, decreasing subset. So take this is the intersection of all this set. So this is actually the limit. That means the every element in the limit in the intersection is actually belongs to the every set. The element in the limit belongs to the every set B1, B2, every B1, Bi. But that does not mean that this belongs to the every AI, because AI may not be decreasing. AI may be anything. AI may be like that. So AI may be say A1, it is say this is A1, and this is maybe A2, and this may be A3, and this may be A4, this may be A5, and so on and so forth. Now, now B1 is the union of all this. Now, what is B2? B2 is just we drop A1. That means we are dropping this part. But other elements are already in A2. That means is in the union of k equal to 2 to infinity. So next we are dropping the A2 part where it is not in other set, or not that. We are dropping this part, and then we are dropping this A3 this part. So what does actually mean? What does actually mean? That means if one element is x belongs to this, then what is the meaning of that? That means x belongs to Bn for all n in natural. So what does mean? So this is for all n. That means this x belongs to actually the union over this for, so x belongs to union over k equal to n to infinity ak. So what is the meaning of that? For all n. That means actually x occur for infinitely many ai. X occur in infinitely many ai. If it is in a finitely many ai, so let some y which belongs to belongs to this y belongs to finitely many ai, what happens? Finitely many a. Then what happens? Or ak. That means some say x belongs to say a10, y belongs to a10, then y belongs to say a13, or the y belongs to the last one, say 1 lakhs 250 is the last one. So because it is finitely many ai, so you just list all ai where the y belongs to. Now there is a maximum index, and after that y does not belongs to after that index. So y does not belongs to ai when I is greater than this. This is the last one. So this is the last one. So this is the last one. So that means what happens? That means y does not belongs to any bi. Bi is the union of this after 1 lakh 215. So for all I is greater than this. So that means y cannot belongs to that intersection. Then that implies actually this implies this, and this implies y is not in the intersection. So y is not belongs to the limit. Limit means the intersection. Now if y belongs to infinitely many ai, so if y belongs to belongs to infinitely many ai, what happens? Infinitely many ai, then what happens? Then that means say y belongs to a1, then y belongs to a5, then y belongs to say a10, then it's not stop. So that means whatever you take, or whatever you k take or n take, whatever for all n in natural number. So you always there is a, so there exists a k which is greater than n, such that y belongs to that ak, because it is infinitely many there. If it is not so, then that means y does not belongs to all a belongs to all ak for k greater than n. That means y belongs to only finitely many ai. It's less than or equal to n many ai's. After that, no ai is not belongs to any set of ai. Now, if y belongs to infinitely many ai, what is the meaning? That means that y belongs to some ak after n. If you n is large, say 1 crore, you again have a say y belongs to say 5 crore 2 lakhs 300, a 5 crore 2 lakhs. If you take say n equal to say 10 crores, then y belongs to some 15 crores 3 lakhs 2050, a 15 crores like that. So, what is the meaning? That means there is. That means if it is belongs to at least one ak, that means y belongs to the union over this. So y belongs to Bn. So there is at least one set, so it belongs to the union. So y belongs to Bn for all n. What is the meaning? That means y is actually in the limit, in the intersection. So it is if and only. So if it is a finitely many, then it can't belongs to the limit. If it is infinitely many, then it is belongs to that intersection. So that means that prove that if y belongs to the intersection of n equal to 1 to infinity, then n equal to k is equal to n to infinity in union, and then a k, which is actually by definition, it is by definition lim sup sometimes like that, n tends to infinity ai an. That if and only if, this actually means that y in y belongs to infinitely many ai. And sometimes this is written in a phrase. That phrase is y is infinitely often. IO means infinitely often. Sometimes called it is infinitely often. Infinitely often. So infinitely often means it belongs to ai for infinitely many ai. So eventually is if for every large value of n, y will be after some that large value of n, y belongs to some in some ak. So that's why it's called limit superior. So limit superior, every element of limit superior actually infinitely often. The elements where the infinitely often is actually in the lim sup. The collection of lim sup is now it is very easy. So so that means your lim sup, which is by definition that this intersection and the union, this is the set of all y such that, or in omega in the set, then y infinitely often. We just write that. Next, what is lim inf? Now, what is lim inf? So lim inf is the other way. So we define lim inf, n tends to infinity. Lim inf, sometimes we write that in lim. Sorry, that's an. This is by definition. First intersection and then union. So again, you just call this as say Bn. Bn is the intersection of all this. You call this as a Bn. Now whatever. Now it is now Bn is an increasing sequence. Clearly, it is increasing sequence. Why? So that means you are taking intersection over all AIs. Then for B2, the intersection over from to start from the A2. Now, obviously, A1 intersection, A2 intersection, is a subset of A2 intersection A3. So you're dropping one set. If you drop one set, intersection will be larger. It's superset. So it is an increasing sequence. So that means Bn increased. And now this limit of Bn is defined as, this limit of Bn is defined as the union. Since it's the increasing sequence, now defined like the union. So say it is a B1. So then it is B2, then B3, dot, dot, dot. So this is the union over all this. If it is increasing sequence, but AI is not the increasing sequence. So that's why we take an intersection, and then it is an increasing sequence. Then we take the union. Now again, what is the meaning of this? What is the meaning of this? If some y belongs to this intersection, what is the meaning? So y belongs to this union intersection, then what happens? That means it is clear that since it belongs to the union, that means there exists and some say some m natural number such that what happens, since there is a union, so y belongs to that bi. This is actually bn, so y belongs to bn. So it is a union of n equal to 1 to infinity bn. So if some element belongs to the union of all these b1 b2 dot, 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 that means y belongs to some m y belongs to bn. Now what is meaning of this? Again, this means y belongs to bn means y belongs to the intersection. That means y belongs to the bk for all k greater than or equal to m. So since it belongs to the intersection, that means it belongs to the bn b. What is bm? Bm is just k equal to m to infinity. So am intersection am plus 1 intersection am plus 2. So that means y belongs to am plus 1 am plus 2 for every n greater than or equal to m y belongs to that set. That means it is eventually there. So after some time, for the y belongs to for the every set of ai in the sequence. So what is the meaning? The meaning is so y belongs to the lim means the same notation. An is just that means y is called eventually or almost something called almost surely, almost. This in probability sense we write almost surely, it's called eventually. Eventually means this. After some time, it will be for every set y belongs to that. For some k after that y belongs to the every set. It's called eventually, or sometimes called y is in y belongs to, or better language, y belongs to a k for all but finitely many k. It is called all but finite. All but finite means it is all except some finite element, some finite all but for all but finite many k, finitely many k. So for finitely many k, y does not belongs to that set. For say 2 or 1 core, maybe 10 cores, but after that y belongs to everywhere. So that means it is eventual. Now it is clear that any element, if it is eventually, after some time it will belongs to the every set. So y is eventually, if y is eventually, then obviously it means it implies that y is infinitely open. Infinitely often. So if it is after some time every set, that means infinitely often. It belongs to the infinitely many set. So what is the meaning? That meaning is y belongs to the limit, then it belongs to the lim sup. What is the meaning? That meaning the lim inf actually is a subset of lim sup. So it is subset. So it is just a subset of this lim sup. Sometimes we write that the increasing ai increasing or an increasing, we sometimes write not decreasing, something like that. Not decreasing, non-decreasing. Non-decreasing is just increasing. Decreasing is non-increasing. So this is the definition, and from this definition we find what elements are in this lim sup and what element are in lim inf. Now, if so possible that lim inf equal to lim so if definition, if lim inf is same as, may or may not be same, it is subset, but if it is same as lim sup, if it is so, then we say limit n tends to infinity an exists, and we call this, we say this limit is just the lim sup or the lim inf, this, because they are same. So if these two are equal, then that is called the limit. That set is called the limit set. Now, just take a special case. Say special case. So take an is increasing. Now, what is the lim sup? What is the lim sup? What is the lim sup? Now, it is increasing. So what is the lim sup? This is increasing. This actually, what is this? By definition, taking first union k equal to n to infinity, and then intersection. Now, if you take the union k equal to 1 to infinity, what is this? So it is increasing sequence. Say this is A1, then it is A2, then it is A3. So what is the union? What is a Bn actually? Bn is by definition, say we call this as a Bn. Now what is B1? B1 is a union of all this. What is B2? Actually, B2 is same as B1, because the A1 is a subset of A2. So if you take the A2 union A3 is the same as A1 union A2 union A3. So A1 union A2 is actually A2. Similarly, A1 union A2 union A3 is actually A3. So that means all our Bn's are equal actually. All Bn's are equal. And since all Bn's are equal, this intersection is just the B1. Just the B1. Just the B1. And what is B1? B1 is the union of all this. So it is just union of k equal to 1 to infinity. And that is, we define like a limit. So lim sup and limit, the previous concept of limit is same. What is the lim inf in this case? What is the lim inf in this case? In the, when this is a increasing sequence. Now we know what is the definition of that. We first take intersection, then we take union. Now what about if it is a increasing sequence? What is the intersection? Intersection is just A1. Intersection is just AN. This intersection is AN. This intersection is AN. Because the intersection of AN, intersection AN plus 1, but AN is subset of every AN plus 1, AN plus 2, AN plus 3, So the intersection is AN. That means this is just the union of this. So it is same. So these two are same. Basically, lim sup and lim are same. So that means if it is the increasing sequence, the lim sup and lim are same. And that is called the limit. Similarly, you can check that if it is a decreasing sequence, then also your lim sup and lim inf will be equal. Similarly, you can check for decreasing sequence. Now, what is the motivation? Why they are defined this? Already we got an idea that if some element are in that collection of set, eventually, almost surely for all but finitely many element, that is the lim soup, and something is infinitely often, then we call is the element of lim inf. So this is the basic idea. Now, what is the is there any connection with the real number, a real sequence? And there is a connection with the real sequence. So consider the real sequence x1, x2, dot 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 is a sequence of real number. Sequence of real. Now, limit may not exist. Same for limit sequence of sets, limit may not exist. But lim soup and limit always exist. So what is the definition of lim soup for a real sequence of real numbers? Now we know the sequence of real number, the lim soup is such a point. Lim soup say it is a lambda. Lambda is a lim soup of this sequence is such a point, you know, this is the highest limit. That means if you take slightly epsilon, so for all epsilon, if you take any small or whatever large, after that in this there is no limit. So no limit point. So that means here there is only finitely many elements. Finitely many elements here. And since it is a limit, that means what happened? That means in this from lambda minus epsilon to lambda plus epsilon, there are infinitely many elements. So what is the meaning of that? That means there are infinitely many elements which is greater than this. So the set of all xn such that xn is greater than this is an infinite set. And xn such that xn greater than lambda plus epsilon for all epsilon positive, this is a finite set. That means that infinitely many elements are in the lambda minus epsilon to lambda plus epsilon. That means that lambda is a limit point. And there is no other limit other than greater than lambda because for every epsilon there are finitely many elements which is bigger than epsilon lambda plus epsilon. So this is the highest maximum limit point. So that is called the lim soup. And similar for the lim inf. Lim inf, if mu is the lim inf, that means after here it is an infinitely many thing and here it is a finite. Finitely many, it is infinitely. That means infinitely many are here. So this is a definition, but there is one more equivalent definition is this. So you first take the maximum of or supremum, maximum may not exist, whatever, you just first take supremum of all ak such that a greater than n, greater than or equal to n. So the sequence is some x1, x2, dot 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 dot, and you have take some n, and then take the supremum over all these elements. Now call this as say yn. Now if you drop one, if you take yn plus 1, that means you are dropping one element. So this is a supremum over this part. Then what happens? If you drop one, then maximum value, the supreme value, may be equal or maybe less. It can't be bigger. If there are 10 elements, if I take the maximum value of the 10 element, and if you're dropping one, the maximum value of the rest 9 element can't be bigger. That means it's a decreasing sequence. Yn is always greater than or equal to yn plus 1. So it is a decreasing sequence. And once it's a decreasing sequence, you know what is the limit of that. This limit of a decreasing sequence is just the infimum of that. infimum over all n. So infimum over all n means it is if it is a decreasing sequence, the infimum actually the limit. If it is an increasing sequence, then the supremum is the limit. So similar idea for this. If you take the first take the infimum, in that case this is the increasing sequence, because you are dropping one more, and then the minimum value will be maybe bigger, or maybe equal. It can't be less. So it is increasing sequence. Now if you take the supremum of that, so it is a limit. So it is just this part is yn. So this is the limit of yn. Now which one is bigger? Infimum, supremum xk, or supremum infimum xk? Which one is bigger? Now to show this, we just name this like that. Say yn is a supremum over all k greater than equal to n xk, and you check Zn as infimum. Now yn must be greater than equal to Zn. It is clear. Now your yn is a decreasing sequence. And your Zn is an increasing sequence. And obviously yn is greater than equal to, the supremum must be greater than equal to the infimum. Now you can easily check that yn is actually greater than or equal to zk for all k greater than n. What is so? What is so? Because say your y10 and you're comparing y10 with the z say 15. Now we know that y10 y is a decreasing sequence, so y15 is less than y10, but y10 is greater than or equal to z10, y15. y10 is greater than or equal to y15 because it's a decreasing sequence. But we know, we already see that y15 is greater than or equal to z15. That means y10 is greater than or equal to z15. And obviously y10 is greater than or equal to z16, z18, like that. So you fixed your n now, fixed n. Now take the limit of, so zk is the increasing sequence, so take the limit. So once you take the limit, fix n, so this will be limit k tends to infinity zk, which is nothing but the limit. Which is nothing but the limit. Why it is a limit? You take the limit. This part, this thing. We do not give the name of this. So this part. So this is this thing, whatever. This is actually this should be going to this mu. So it's called say alpha. So this is nothing but this is alpha. So you're taking infimum, then take the supremum. Supremum is actually limit. So that means your yn is greater than or equal to alpha for all n. Now taking limit for y, and y is a decreasing sequence. Okay, so limit n tends to infinity is just the supremum. Sorry, it is infimum. So that is called a beta. That is called a beta. It is just the infimum, which is beta. It's greater than or equal to alpha. So we prove that is beta greater than or equal to alpha. So that means infimum, first supremum, then infimum over xk is actually greater than or equal to, if you take infimum first and then take supremum, this will be less. And actually this is nothing but lim-inf. You can easily check that this is lim-inf, and this is actually lim-sup. So this is lim-inf, the right hand side is lim-inf, and this is lim-sup. Actually this is that lim-sup and lim-inf. The supremum and the infimum, then supremum is the lim-sup, lim-inf, and then supremum first, then infimum is lim-sup. So is equivalent definition. You can define lim-sup in two different ways. You can say, okay, it is a limit which is the maximum value, the maximum among the limits, or you can say it is a is such a numbers that if we add something, some positive thing, after that there is only finitely many thing, and if you just less minus something, subtract something positive number, then bigger after that, the bigger than that is infinitely many values. And you can say like that also, that value is like taking supremum and then taking the infimum over that. So actually this idea motivated from this, and from this motivation in real line, real sequence, this lim-sup and lim-inf, we actually motivated from that, and we define the same thing in set also. For a set we define like that. So in that case supremum infimum is not there. So supremum, it is actually means the union, then infimum is actually intersection. And this is, which is bigger than, is a superset of lim-inf, and which is defined like that. So infimum first take infimum, that means first take intersection, and they take union. So similar definition. So you just replace infimum with just by intersection. Obviously, here infimum means it is a sort of the minimum thing, and intersection means is also some sort of minimum among the all sets. So that definition of this lim-sup and lim-inf in the sequence of set is actually just the generalization of this concept of lim-sup and lim-inf in the real sequence. So this is the basic idea of lim-sup and lim-inf and the sequence limit of the sequence, and we will use this thing later. One more basic technique of dealing with this sequence of set is like that. If you ever say sequence A1, A2, dot 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 dot, A3, it may be decreasing, maybe increasing, maybe anything, maybe whatever. This is A, this is maybe B, whatever. Okay, just first take this is the increasing sequence. Okay, first set is the increasing sequence. So that means your A1 is a subset of A2, A2 is a subset of A3, so on. Now what is a Venn diagram? So it is A1, say superset A2, then superset A3, increasing that. Now there is one technique. We define B1 as a, say, A1. So this is my B1. Now B2 we take A2 minus A1. So that means this is my B2. And we choose B3 like A3 minus A2. So what is this? This part, B3. It's red part. If we define like that, then we can easily see that two things. Number one, B1 are disjoint, BI's are disjoint. That means BI intersection BJ is phi for all I not equal to J. If I not equal to J, then this intersection is phi, so it is disjoint. And one more extra thing is the union over all these BI's is actually union over all this AI. You can easily check where taking a element from the union of BI, you can easily show that it's the element of AI because BI is a subset of AI. What a definition of BI, what we define like that. So Bn is actually a subset of AI. So one side is easy. So union over BI must be subset of AI, union over AI. Other side is also trivial. If you take any element in the union, that means it belongs to some AI. So if you take a element in the right hand side, what is the meaning? If you take the one element from a union of AI, that means actually there exists and some n or some m in natural numbers such that x belongs to that am. Now, is x belongs to bm? May not be. May not be. Now, you just check whether x belongs to a1 or not. Whether this x belongs to a1, whether this x belongs to a2 or not. So if x belongs to a1, done, because x belongs to a1 means x belongs to b1. That means x belongs to the union of bi. Now, if so happen, if the x does not belongs to a1, but x belongs to a2, then what happened? Then actually x belongs to b2. b2 is actually a2 minus a1. X belongs to a2 but not in a1. So actually you have to find the minimum index, minimum suffix for which x belongs to an. So minimum such n. You just find the minimum of such n, that n set of all n such that x belongs to n. You take the minimum of all this n. Find the minimum. Now minimum exists because this is non-empty set. Remember, this is non-empty set because there is at least one m for which this x belongs to m. So m must be there. So this is non-empty set, and non-empty set, these are the minimum. This is a set of subset of natural numbers, so it is a minimum. And that minimum, if you take that minimum, say if minimum is say r, then x belongs to ar, br, because x belongs to ar, but it does not belongs to ar minus 1. So this is a very important thing to find some probability because we need to disjoint. So that is the idea of taking a increasing thing into the disjoint part. But for decreasing, you can't do this. If it is a decreasing thing, say b1, say a1, then if it is a2, can you do this? Yes, we can do this. We can take this part as a b1. b1 is actually a1, a2 minus a1 minus a2. Then b2 is just a2 minus a3. And in that case, these are disjoint. But what we is actually now you get nothing. It's a disjoint, but the union is actually a1. Again, this union of AIs are A1 and union of BIs is also A1. So we know the union is A1. So why we write union AI in this union form? But here we don't know what is a union if it is increasing sequence. That in the union is not of some AI. Union of this set, this all collection of set is not some A100 or A50 or A155 crores. Not that. But if you are decreasing, then union is just the first set. Union you can write is a single AI. But if it is increasing, you can't write that. So that's why you need this. And for decreasing sequence, we do the reverse thing. If it is a decreasing sequence, we don't do this. It's not useful. You can do this, but it's not useful. Not useful. The idea is if it's a decreasing sequence, if n is a decreasing sequence, then we take the complement. And complement is the increasing sequence. And we find the union of the complement. We find the complement thing, and then get to the if you want to find the probability, then you go to the complementary set. This is the basic idea. So we do this for the increasing sequence, and for the decreasing sequence, we take the complement. It's in our increasing sequence. We find the result on. We use the theorems on the increasing sequence, and then we find the what is result is, or what is the theorem for the decreasing sequence. Now, if the sequence are not increasing or decreasing, whatever, now we do the same thing, same trick. If it is any arbitrary collection, may not be increasing or decreasing, we first consider this B1 like a B1 A1, then B2 like A1 union A2. We take this this thing. Now this B1 and B2 are now this Bn's are now increasing. And so once if Bn is increasing, we do the same thing. Then we find Cn, which is Bn minus Bn minus Bn plus or minus B. No, Bn minus Bn minus 1. And that Cn is now disjoint. So you have to two step. We need a two step. If it is not a decreasing or increasing, it is or maybe may not be disjoint. Anything. So it's just first take the unions, then their difference, then we get a disjoint set. So this is the basic thing, basic techniques to deal the sequence of sets. In next class, we discuss on the Borel sets and Borel sigma algebra, and we find why these Borel sigma algebra are important. We see what is sigma algebra. We've already seen in the first class what is sigma algebra. It's a collection of some subsets, which empty set and this whole set is there. If A is there, then A complement is there, and if the sequence of sets, so these two things, if there's phi set is there in the sigma algebra, then if A is in there, then implies A complement is there. Second and third one is if A1 dot 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 is a sequence of set comes to the sigma algebra, there union is also in sigma algebra. Now this may not be increasing or decreasing, whatever. This may be any arbitrary subset. Now these three actually give the sigma algebra, definition of sigma algebra. Now what is the least such a sigma algebra? The smallest sigma algebra is just you take sigma algebra over say on omega, the whole set, universal set. The smallest sigma algebra is smallest sigma algebra is just the is collection of two sets only. You have to take the phi and their complement. And what is the largest? Largest sigma algebra is a power set. Now, if we want to find the sigma algebra on R, real number, set of real number, so the power set of R is a very large collection. And in power set of R, you actually can't define the length or this sum of measure. So there is a problem, there is a contradiction. If you want to define some measure on the power set, that leads some contradiction. So that's why, and if you define a measure or probability in this smallest set, that is not interesting. So we have to find some in between something. So it is not the all power set or all subset, collection of all subset, not a power set. We left some say, we dropped some sets, some complicated thing. But we also take some large class, not the very few subset. We take a large number of collection. We take a large number of say subset of real number. Actually, we take all the known subset, and that two sigma algebras are there. One is called Borel sigma algebra on R, and one is called Lebesgue sigma algebra. The two sigma algebra. We deal with the Borel sigma algebra. The Lebesgue sigma algebra is not in the syllabus. And this Lebesgue sigma algebra, the major difference on Lebesgue sigma algebra is the ultimate. Nobody till now generalize this Lebesgue sigma algebra after that. So if there are some sets which is not in the Lebesgue sigma algebra, we can't define measure there. But between Borel and Lebesgue there is a huge gap. There is large number of subset of real number which is not a Borel but Lebesgue. But these sets are very complicated. If I want to find a set which is Lebesgue in the Lebesgue sigma algebra but not in the Borel sigma algebra, finding that set is very hard. Unless one is genius, no one can find in his life, in her life. So this set exists. There are many sets, but finding that set is very complicated. Actually, this finding the set is not in the MSc in syllabus in any institute. So that means we just we know, if you consider only Borel sigma, we know we lost the several sets, subset of real number, which is Lebesgue but not Borel. But this loss is not actually important because we don't know what you are losing. What you are losing, what sets are not Borel but Lebesgue, that losing set, well, you lost the set, that is very complicated, and that we don't deal with this. So we lose huge amount of set, but these sets are actually not useful. So that's why you consider only the Borel sigma algebra. And next class we see how Borel sigma algebra is constructed. It is a constructive way. We take some sets in a Borel sigma algebra, then from that set we construct what are the other set in this Borel sigma algebra. So this is for today.